For 2,000 years, an impossible machine lay broken beneath the sea, mistaken for little more than corroded debris. Nothing about the object looked like a computer. It looked like a stone fused with green-black bronze. The object came from a Roman-era shipwreck, loaded with art, luxury goods, and scientific knowledge from the Greek world. Greek sponge divers found the wreck by accident around 1900, beginning the first major underwater archaeological recovery. The divers raised statues, pottery, coins, and one fragile mass whose real importance, documentary, remained hidden. Among spectacular sculptures, the small bronze fragments attracted little attention at first. Then a crack revealed something no natural rock should contain: a precisely toothed wheel. The lump was not decoration. It was the remains of an intricate mechanical calculator. A single turn could transmit motion through a network of gears and transform time into positions on the sky. This machine could model astronomical cycles, track calendars, and predict eclipses more than 2,000 years ago. Only about 1/3 of the original mechanism survives, divided today into 82 fragments. The largest fragment preserves the machine's structural core and the most recognizable surviving gear. Understanding it took generations, because corrosion hid the mechanism's internal structure and most of its inscriptions. Early scholars first called it an astrolabe, a navigation instrument, or a mechanical calendar. Later researchers realized the fragments contained a clock-like gear system far more complex than expected. X-rays made the invisible machinery visible, allowing researchers to count teeth and trace gear trains. Modern computed tomography later uncovered thousands of characters that had remained unread for nearly 2 millennia. The inscriptions were not decoration. They described displays, cycles, and instructions for operating the machine.
The original device was housed in a wooden case, with dials and instructions on both sides.
Its power source was simple: a human hand turning a crank. The computation happened mechanically. The gears were bronze, thin, and hand-cut, with triangular teeth rather than modern clock profiles. Every wheel required careful layout, cutting, filing, and fitting, with the tools available in the Hellenistic world. The challenge was not merely making gears. It was fitting many calculations into a compact, layered machine. The surviving fragments suggest a device only about the size of a small box, yet packed with linked cycles. Nested shafts could carry different motions to several pointers sharing the same central display. The front display combined a calendar ring with the zodiac, turning dates into celestial positions. Set the date, turn the crank, and the entire mechanical sky advances together. The front dial displayed the sun and moon against the calendar and zodiac. A small rotating sphere could show the moon's changing phase as its position shifted relative to the sun. The phase display was a mechanical calculation of the changing angle between the sun and moon. But the Moon does not move across the sky at one perfectly constant speed. The mechanism modeled that irregular motion with an ingenious pin and slot system. As the pin moved through the slot, the moon pointer alternately accelerated and decelerated. This translated an ancient theory of the moon's unequal motion into physical bronze. The mechanism also accounted for the slow rotation of the moon's orbital anomaly over several years. On the back, a 5-turn spiral tracked the 19-year metonic cycle. After 19 solar years, the phases of the moon returned to nearly the same calendar dates. The gears converted that long relationship into a repeatable mechanical calendar. Additional cycles refined the calendar, correcting the small mismatch that accumulates over decades. The back of the mechanism carried 2 major spirals, one for the calendar and one for eclipses. The lower spiral tracked the Saros, a cycle that brings similar eclipses back after 223 lunar months. When the pointer reached an inscribed cell, the machine indicated that an eclipse was expected. The inscriptions distinguished solar from lunar eclipses and encoded details about their expected appearance. Tiny notes could describe timing, direction, and other characteristics associated with an eclipse event. A Saros repeats eclipse geometry, but Earth's rotation shifts where the event is visible. A longer exoligmos cycle helped correct the time of day shift across 3 Saros periods. One hand-powered input coordinated calendars, lunar motion, and eclipse cycles across the entire machine. The mechanism compressed decades of astronomical knowledge into a device that could be explored in minutes. Its eclipse mathematics drew on long cycles known from Babylonian astronomical observation. Greek mathematicians transformed those cycles into geometry, ratios, and finally moving machinery. The machine also tracked the 4-year cycle of major Greek athletic festivals. Its inscriptions name festivals including Olympia, Isthmia, Nemea, and Pythia. For its owner, astronomy, calendars, civic life, and sacred festivals belong to one connected system. The covers carried a technical description of the displays, almost like instructions engraved onto the machine itself. The surviving text describes a front display of the ancient Greek cosmos, including the known planets. But the front mechanism is the most damaged part, so its complete design remains debated. Different reconstructions can fit parts of the evidence, especially where gears and pointers are missing. A successful model must match the physical fragments, the tooth counts, the available space, and the inscriptions. Modern teams have proposed compact planetary gearing that recreates the ancient order of the heavens. If the reconstruction is broadly correct, the front was a moving mechanical cosmos. The mechanism reflected the geocentric astronomy of its time, a moving sky organized around Earth. Planetary motion includes apparent reversals, making a complete mechanical display extraordinarily difficult. Ancient Greek models explained these reversals with combinations of circles moving on circles. A gear system could translate those geometrical circles into the motion of a pointer. X-ray readings preserve long cycle numbers, linked by one reconstruction to Venus and Saturn. The known planets were Mercury, Venus, Mars, Jupiter, and Saturn, each with a different repeating pattern. Any planetary system had to fit many motions into extremely limited mechanical space. That is why reconstructions are tested not only mathematically, but mechanically. The parts must actually fit and turn. The surviving evidence supports remarkable sophistication, but some details of the original front remain unresolved. The mechanism is both understood and mysterious. Its core functions are clear, while its complete form is still being rebuilt. The mechanism emerged from a Mediterranean world where astronomy, mathematics, engineering, and trade crossed borders. Who designed it remains uncertain, and several centers or intellectual traditions have been proposed. Its maker combined theoretical astronomy with the practical knowledge of a highly skilled bronze workshop. Every gear ratio encoded a numerical relationship between cycles in the sky. The machine appears to combine Babylonian cycles, Greek geometry, and an Egyptian-style calendar ring. It was not an isolated miracle. It was a synthesis of knowledge accumulated across cultures and centuries. The device may have served teaching, demonstration, calculation, prestige, or several purposes at once. No surviving text tells us exactly who owned it or how often it was used. Its final journey placed it among valuable cargo moving through the late Hellenistic Mediterranean. The ship was probably carrying Greek goods toward wealthy Roman markets when disaster struck. Justing than sense. Statues, pottery, coins, timber, and the mechanism entered a cold, corrosive underwater archive. The wooden housing vanished, bronze plates fractured, and corrosion slowly welded gears into mineral masses.
Most of the original machine disappeared, leaving researchers to reconstruct a complex whole from scattered remnants.
Every modern reconstruction is therefore a negotiation between hard evidence and carefully limited inference. The goal is not to build the most spectacular machine, but the simplest one that explains the evidence. When a model aligns with the fragments, inscriptions, and mechanics, it becomes a testable historical hypothesis. Working replicas let researchers test whether proposed gear trains can move without jamming or contradiction. A successful reconstruction must reproduce the cycles described by the ancient machine. Today, computer models and physical replicas work together to explore a computer built without electronics. Nothing else of comparable surviving mechanical complexity appears for many centuries after the Antikythera Mechanism. But the gap does not mean ancient engineering vanished completely. Most machines were recycled, decayed, or never preserved. Bronze was valuable, wood rotted, and complex instruments were unlikely to survive by chance. The mechanism survived precisely because a shipwreck removed it from the normal cycle of reuse. It may be the lone survivor of a broader tradition of sophisticated Greek mechanical astronomy. That possibility changes the question from "how was this possible?" to "how much has been lost?" New imaging can still recover details from fragments already studied for more than a century. Each newly read character or tooth count can strengthen one reconstruction and weaken another. The history of the mechanism is also a history of changing scientific interpretation. The machine keeps teaching because its fragments force historians, astronomers, engineers, and classicists to work together. Calling it a computer does not mean it resembled a laptop. It means the device mechanically processed inputs into outputs. A chosen date became a network of calculated astronomical positions and cycle indicators. It belongs to the long history of analog computation, machines that represent quantities through physical motion. The mechanism pushes the history of complex computation much deeper into antiquity. Unlike a static chart, the machine let its user explore changing celestial patterns by turning a handle. It was a manipulable model, an ancient interface for asking, "What happens when?" That makes education a plausible purpose. The machine turned difficult celestial cycles into visible motion. It may also have been a prestige object, demonstrating wealth, learning, and technical mastery. Prediction and calendar planning may have mattered, but the device was probably more than a single-purpose tool. Without its owner, workshop, or complete front display, some questions may never receive a final answer. Yet the surviving machine already reveals an astonishing idea. The sky could be calculated with gears. Inside a portable box, ancient engineers compressed generations of astronomy into bronze motion. Fragments, scans, inscriptions, mathematics, and replicas now work together to reconstruct the lost machine. Turn the crank, and a date becomes a moon phase, a celestial position, and an eclipse prediction. Its complexity was not magic. It was the result of observation, mathematics, craftsmanship, and connected cultures. From 82 fragments, researchers recovered a machine that changed what we thought ancient technology could do. It predicted the sky not by prophecy, but by encoding celestial cycles into ratios of bronze teeth. A small island gave its name to a machine that expanded the known boundaries of the ancient world. The object pulled from the sea was not an impossible computer. It was evidence of a lost mechanical tradition. And inside that corroded fragment, the ancient sky is still waiting to be read. The room is new. The conversation is new. Yet for one impossible second, your brain insists this has happened before. That certainty arrives before evidence. You feel recognition, even while knowing you have never entered this place. Déjà vu can feel physical. A pause, a chill, a tightening attention, as if reality briefly slipped out of sequence. You search for the original memory. A dream, a photograph, another room, but the source refuses to appear. Then the feeling collapses. The room becomes ordinary again, leaving only the question of why it felt so certain. The name comes from French, déjà vu, meaning already seen. But the experience is larger than vision alone. People described strangely familiar moments long before neuroscience gave them a modern name. Different cultures have linked the feeling to dreams, spirits, fate, past lives, or moments repeating across time. Science does not require a hidden timeline. It begins with something more ordinary and more mysterious: memory making an error. The central puzzle is simple. How can the brain produce recognition without retrieving anything documentary that was actually remembered? Memory is not one system. A moment can feel familiar even when you cannot recall where, when, or why. Familiarity is fast and vague. It tells you something has been encountered without reconstructing the encounter itself. You know the face, but not the name. You recognize the street, but cannot remember the visit. Recollection is slower and richer. It rebuilds details, the person, the place, the sequence, and the surrounding story.
In ordinary déjà vu, familiarity surges, while recollection fails to identify a legitimate source.
At the same time, another part of the system knows the present is new. That is what makes the feeling uncanny. Déjà vu is not a full memory replay. Usually there is no precise earlier event you can inspect. It is also different from simply remembering incorrectly. The person often recognizes that the familiarity itself is inappropriate. That awareness may be the key. The eerie sensation could emerge when memory catches its own contradiction. Instead of proving memory is failing completely, déjà vu may reveal that its quality control system is still working. Researchers often look to the medial temporal lobe, a memory network buried deep behind the temples. Structures near the hippocampus help judge familiarity, context, and relationships between parts of an experience. There is probably no single déjà vu switch. The experience may emerge from several memory and monitoring systems interacting. In clinical settings, electrical stimulation of temporal regions has sometimes evoked déjà vu-like experiences. But provoking a feeling does not prove. Every everyday episode begins in exactly the same place. One old idea proposes a tiny processing delay. The same event reaches awareness twice, documentary, making the second arrival feel remembered. Another possibility is a false positive in recognition. The brain's familiarity detector briefly fires for a genuinely new event. Novelty matters because déjà vu contains two judgments at once. This feels known, and this should be new. Recent accounts emphasize that conflict itself, the disagreement between familiarity and novelty, may generate the distinctive feeling. Even this is not a final answer. Déjà vu is probably a family of experiences, with more than one root. One of the strongest experimental clues comes from places that are new in detail, but familiar in structure. A hotel lobby can resemble a childhood school. A new alley can echo the geometry of a street seen years ago. The resemblance may remain below conscious recall. You detect the pattern, but cannot identify the earlier scene. Researchers test this idea with virtual environments, where room layouts can be controlled while surface details change. Participants first explore several scenes without knowing which spatial patterns will return later. Later, they enter new-looking scenes. Sometimes the arrangement secretly matches a scene they can no longer recall. Reports of déjà vu become more likely when the new scene maps onto an unrecalled earlier layout. The trigger does not need an exact copy. A partial structural echo may be enough to create familiarity without identification. That helps explain why déjà vu often feels connected to a place, even when no remembered place comes to mind. Spatial similarity explains some laboratory episodes. It cannot yet explain every spontaneous moment in ordinary life. Déjà vu often carries another illusion, the feeling that you know what will happen in the next few seconds. Experiments can test that confidence by asking people to predict the next turn while they are experiencing déjà vu. The feeling becomes stronger, but prediction accuracy does not reliably improve beyond chance. Your brain may confuse familiarity with foresight. If the moment feels repeated, its ending seems as though it should already be known. After the event, hindsight can make a vague impression feel more precise than it originally was. Memory is reconstructive. It does not replay the past. It rebuilds a useful story from fragments. Déjà vu also increases curiosity. The mind wants to identify the missing source and resolve the contradiction. That search can create false connections, because the brain is exceptionally good at finding patterns, even incomplete ones. This is why past lives, parallel worlds, and precognition can feel persuasive. The experience arrives with certainty before explanation. Science can respect the intensity of the feeling without treating the feeling itself as proof of a hidden reality. Another proposal begins with attention. Perhaps part of a scene is registered briefly before conscious awareness catches up. A fraction of unnoticed perception could make the full experience feel older than it really is. Documentary remembered. Laboratory studies show that previous exposure can influence familiarity even when the original encounter is not consciously remembered. Repeated exposure can make something feel safer or more familiar. But déjà vu includes the extra awareness that familiarity is wrong. An attention lapse might therefore contribute in some cases, without explaining episodes triggered by complex places or thoughts. Many explanations survive because déjà vu is brief, unpredictable, and difficult to capture at the exact moment it occurs. Dreams offer another tempting source. A new scene may resemble a dream whose details were mostly forgotten. But remembering a dream after the event is vulnerable to reconstruction. The present can reshape what you think the dream contained. Déjà rêvé is the specific feeling that the present was previously dreamed. It is related, but not identical, to déjà vu. These overlapping experiences suggest that one label may hide several different memory events. Ordinary déjà vu is widely reported by healthy people. A brief episode by itself is usually not evidence of disease. People describe it during conversations, travel, reading, music, and completely routine moments at home. Some studies find that people who travel more also report more déjà vu, though correlation does not establish the cause. Novel environments may offer more chances for partial resemblance, new details arranged in patterns your memory has seen before. Fatigue, stress, and distraction are often blamed, but their exact role in ordinary déjà vu remains less settled than popular claims suggest. Most ordinary episodes are fleeting. The intensity can be striking even when the experience lasts only seconds. Some people encounter it rarely, others notice it repeatedly. Frequency alone still needs context.
A short, familiar feeling with full awareness is different from an episode that includes confusion, fear, strange smells, or lost time.
When episodes become frequent, prolonged, distressing, or arrive with neurological symptoms, professional evaluation becomes reasonable. The medical connection matters because déjà vu can also occur as part of focal seizures, especially involving temporal memory networks. Neurologists have associated déjà vu-like auras with temporal lobe seizures for more than a century. A seizure-related episode may feel more intense, emotionally charged, dreamlike, or unusually specific than common déjà vu. Yet people cannot always distinguish seizure and non-seizure déjà vu from the feeling alone. Doctors therefore ask about awareness, duration, fear, bodily sensations, smells, sounds, and what happens immediately afterward. Some focal seizures include a rising sensation in the abdomen, sudden fear, unusual odors, or impaired awareness. Electrical stimulation has reproduced déjà vu-like feelings in some patients, linking the experience to specific brain networks. This does not make ordinary déjà vu a miniature seizure. Healthy and clinical experiences can overlap without being identical. Another clinical phenomenon, déjà vécu, can involve persistent conviction that entire events are being relived. Persistent experiences may appear in some neurological or psychiatric conditions and deserve a different explanation and response. The same words can describe very different events. Duration, insight, symptoms, and context determine what the experience means. Jamais vu his contralicisten's alla de strangen de transitions, to nefien Kate teen proti de sanctions. Key. Repeating a common word many times can temporarily make its spelling and sound feel unreal. Laboratory repetition can produce jamais vu-like unfamiliarity, revealing that familiarity is actively maintained, not permanently attached. Jamais vu is not simply the exact opposite of déjà vu, but both expose how unstable the feeling of knowing can be. Related experiences can involve sounds, voices, movements, or entire situations, not only things literally seen. Déjà entendu describes something heard as if heard before, while déjà rêvé points specifically toward a remembered dream. Because dreams are fragmented, they can supply countless shapes and emotions that later appear to match real life. Once a match is noticed, the dream may be remembered as more accurate than it originally was. Déjà vu belongs to meta-memory, feelings about memory, rather than the recovered content of memory itself. The brain constantly estimates whether information is known, even when it cannot explain the basis of that estimate. A tip-of-the-tongue state is another example. You know that you know, while the missing word remains inaccessible. These feelings are useful shortcuts. Most of the time, they guide memory efficiently without demanding a complete search. Metacognition adds another layer. The mind evaluates its own confidence, errors, and uncertainty. That self-monitoring may explain why déjà vu feels wrong. At the same time, it feels certain. Scientists can induce déjà vu-like states, but laboratory versions may capture only part of the natural experience. Researchers must often rely on self-report. The participant decides whether the strange feeling truly occurred. Brain imaging is difficult because the episode is brief, unpredictable, and altered by the attempt to observe it. So Prasad-Seemly can time resolutionations the Noexisacantissina generalization, timed limited generalization to the individual differences add more noise. The same prompt may trigger wonder in one person and nothing in another. The best explanation may combine several layers: hidden similarity, familiarity errors, novelty monitoring, attention, and personal context. Déjà vu is memorable precisely because it interrupts ordinary certainty. The contradiction forces attention onto a moment that would otherwise disappear. Surprise and emotion can strengthen the later memory of the episode, even when its original cause remains documentary unknown. Each retelling can simplify the uncertainty. A vague feeling becomes a perfect replay, a coincidence, or a prediction that came true. Online, the strangest stories travel farther than ordinary episodes that lasted 2 seconds and meant nothing. Repetition then makes an explanation familiar. A popular story can feel true simply because you have encountered it many times. There is no scientific evidence that ordinary déjà vu proves past lives, parallel universes, or a timeline line repeating. Modern physics describes strange possibilities, but it does not predict that a brief personal familiarity error reveals another universe. The brain itself is a prediction machine, constantly using past patterns to anticipate what the present should look like. Some researchers suspect interrupted prediction may contribute to déjà vu, but this account is still developing. A compressed pattern from the past may fit the present just well enough to feel familiar, but not well enough to be recalled. Memory was not designed as a perfect archive. It evolved to recognize, predict, and guide action quickly. Déjà vu may be one visible cost of that efficiency, a rare moment when generalization produces the wrong familiarity signal. Yet the mistake is noticed. The brain does not simply accept the new moment as a genuine memory. That may be the least frightening interpretation. The strange feeling could be evidence that your memory system caught its own error. When déjà vu happens, there is usually nothing to solve. The source may never become consciously available. If episodes are frequent, prolonged, or accompanied by altered awareness or unusual sensations, recording the context can help a clinician. A fleeting episode with full awareness is common. A pattern involving lost time, seizures, or persistent distress deserves attention. Science has narrowed the mystery, but it has not reduced every episode to one circuit, trigger, or theory. The most likely answer is not that time repeated. It is that memory, novelty, and awareness briefly disagreed.
Déjà vu feels like a door into another timeline. It may actually be a glimpse of the brain checking the boundary between now and memory.
Beneath every ocean, continent, and city, Earth may be storing an astonishing amount of water hundreds of kilometers underground. But this is not a liquid ocean in a cavern. The water is chemically locked inside solid minerals. At these depths, water exists mainly as hydrogen bound into crystal structures, not as free-flowing lakes or seas.
The most important zone lies roughly 410 to 660 kilometers below the surface.
Geologists call it the mantle transition zone, a pressure-built layer between the upper and lower mantle. This hidden reservoir matters because Earth's surface ocean and deep interior are part of one extremely slow water cycle. Water can travel downward with sinking tectonic plates, disappear into minerals, and return through melting and volcanoes. The difficulty is obvious. No drill can reach anywhere close to the transition zone. So scientists investigate this water indirectly, using seismic waves, laboratory pressure experiments, and rare minerals carried upward from depth. Then one tiny diamond inclusion provided the first direct sample from this hidden reservoir. To understand that discovery, first strip Earth into the layers pressure creates beneath our feet. The shallow upper mantle is dominated by olivine, a mineral with relatively limited capacity to store water. As pressure rises with depth, the same chemical ingredients rearrange into denser crystal structures. Near 410 kilometers, olivine transforms into wadsleyite, a mineral that can hold far more water. Wadsleyite does not contain underground droplets. It stores hydrogen inside defects in its crystal lattice. Deeper still, wadsleyite changes into ringwoodite, another high-pressure mineral with major water storage capacity. At about 660 kilometers, ringwoodite breaks down into minerals that generally hold much less water. That sharp drop in storage capacity can force water out and help create tiny amounts of melt. The transition zone may therefore act like a deep sponge, and, at its boundaries, like a water trap. But a mineral's capacity to store water does not prove the entire global layer is filled to that capacity. Because the transition zone is unreachable, scientists read its properties through the way seismic waves travel. Abrupt mineral changes at 410 and 660 kilometers create seismic discontinuities that geophysicists can detect. Seismic tomography converts thousands of travel times into images of faster, slower, colder, and hotter mantle. Their depth, sharpness, and local variations reveal temperature, composition, and possibly the presence of water or melt. Some low-velocity layers near the transition zone boundaries are consistent with small amounts of partial melt. Laboratories test that interpretation by recreating deep Earth pressures and temperatures in diamond anvil cells. When hydrous ringwoodite transforms under lower mantle conditions, experiments can produce melt between the new mineral grains.
Seismic observations beneath North America found velocity drops where mantle flow models also predicted downward movement across 660 kilometers.
Together, experiments and seismic data support dehydration melting as one way water may remain trapped near the transition zone. Still, seismic signals and experiments were indirect. Scientists needed a piece of the deep mantle itself. The crucial sample came from a rough diamond recovered near Juína, Brazil. Deep source eruptions had carried the diamond upward fast enough to preserve a mineral formed hundreds of kilometers below. Inside the diamond was a microscopic inclusion, too small to see without specialized instruments. X-ray diffraction identified the inclusion as ringwoodite, the mineral expected in the lower part of the transition zone. It was the first reported terrestrial occurrence of this high-pressure olivine polymine polymorph in a natural sample. Infrared spectroscopy showed that the inclusion was water-rich, in the mineralogical sense. It contained substantial hydroxyl. The preserved inclusion indicated roughly 1 weight% water locally within the transition zone mineral. That was direct evidence that at least part of the transition zone is hydrous, not proof that the whole layer is equally wet. The diamond solved one question and sharpened another. How representative was that tiny piece of deep earth? A speck inside a diamond had transformed the debate from pure theory into direct observation. The discovery was widely described as an ocean in ocean inside Earth, but that phrase can be deeply misleading. The mineral stores water as hydroxyl, hydrogen bonded within the crystal, not liquid water filling open space. Hydrogen can substitute into defects where metal ions would otherwise occupy the structure. Each grain stores only a small fraction by mass, but the transition zone contains an enormous volume of rock. Across a planetary shell, even 1% water would represent a quantity comparable to vast surface reservoirs. Experiments show wadsleyite and ringwoodite can hold several percent water by weight under suitable conditions. If the entire zone were near saturation, its capacity could equal several surface oceans, but that is a hypothetical upper limit. The real mantle is almost certainly uneven. Wetter near some subduction systems, drier beneath other regions. Where tectonic plates carry hydrated rock deep into the mantle, local transition zone water may become concentrated. Temperature, iron content, mineral chemistry, and mantle flow all change how much water these crystals can hold. Water changes electrical conductivity, seismic speed, strength, and the way mantle rock deforms. Even when hidden inside crystals, hydrogen can make mantle minerals easier to deform over geologic time. That means deep water can influence mantle convection and the long-term movement of tectonic plates. The deep cycle begins when surface water reacts with oceanic crust and becomes stored in hydrated minerals. Sediments, altered crust, and hydrated mantle rocks can transport water toward a subduction zone. As the plate sinks, rising heat and pressure destabilize many water-bearing minerals. Much of that water escapes at shallower depths, helping generate magma beneath volcanic arcs. Volcanoes return part of the subducted water to the surface through magma and gas. But not all water returns immediately. Some hydrated material survives and continues much deeper. Inside the transition zone, wadsleyite and ringwoodite provide new crystal structures capable of storing that hydrogen. The result may be localized reservoirs shaped by ancient slabs, mantle circulation, and mineral reactions. When hydrated material crosses a boundary into minerals with lower storage capacity, water must move somewhere else. Some enters melt, some may migrate upward, and some can be recycled back into the transition zone. This is the deep water cycle, a circulation measured not in days, but in millions of years. Its pace is almost unimaginable, yet over Earth history, it can move enormous quantities between surface and interior. At the base of the transition zone, ringwoodite transforms into bridgemanite and ferropericlase. Because these minerals hold less water, the transformation can trigger dehydration melting. A 2014 study combined high-pressure experiments, seismic imaging, and mantle flow models to test this process. The observed pattern was consistent with partial melt forming where hydrated transition zone material moved downward. Even a very small melt fraction can strongly reduce seismic velocities and change how the boundary appears. If melt rises back upward, dehydration melting could help keep water concentrated inside the transition zone. Together, melting at both boundaries may create a long-lived geochemical filter around the deep reservoir. A similar release may occur when hydrated wadsleyite rises above 410 kilometers into shallower olivine stability. This does not prove a continuous global ocean. It describes mineral-bound water, possible melt, and a highly variable mantle. Every estimate of deep water depends on combining evidence that sees the mantle in a different way. Electrical conductivity can increase when hydrogen is present, but temperature, melt, and composition can produce similar signals. Seismic data also require interpretation. Slow waves may indicate water, melt, documentaries, high temperature, or chemical differences. The mantle is heterogeneous, so one region cannot automatically represent the entire planet. The diamond is direct evidence, but it is still one tiny sample from one locality. Even the diamond's source history depends on models of deep eruption, mantle flow, and mineral preservation. As a result, published estimates of the transition zone's total water content still span a wide range. New deep diamonds, better experiments, and denser seismic networks can gradually narrow that uncertainty. Future maps may reveal whether deep water forms broad reservoirs, narrow slab-fed zones, or a constantly shifting patchwork. The answer will probably be dynamic, because mantle water moves with a planet that never stops convecting. Water weakens mantle minerals, changes viscosity, and can redirect how heat and material circulate. That links deep water to plate tectonics, mantle mixing, and the generation of magma. Water helps rock melt at lower temperatures, making it a powerful ingredient in magma production. Volcanic degassing returns deep water to the atmosphere, where it can eventually rejoin rivers and oceans. Surface water then enters new crust, rides tectonic plates, and begins the journey downward again. The surface ocean is visible and fast-moving. The deep reservoir is hidden and geologically slow. Over billions of years, Grevenst exchange between them may help shape the long-term stability of Earth's water budget. Earth's oceans did not evolve separately from the mantle. The planet's interior has always been part of their history. A planet's mineralogy and deep water cycle may help determine whether water stays at the surface, enters the interior, or escapes. For Earth, the transition zone may be a bottleneck that stores water and controls how easily it crosses into deeper layers. Its mineral phase turns pressure boundaries into valves in the deep water cycle. The story is not an underground sea. It is a planet-sized chemical circulation through solid rock. Its central reservoir lies in the mantle transition zone, between 410 and 660 kilometers deep. Wadsleyite and ringwoodite can store hydrogen in crystal defects at concentrations far above shallow mantle olivine. A diamond from Brazil provided direct proof that at least one part of this zone held substantial water. But one local sample cannot tell us how wet the entire transition zone is. Scientists therefore combine diamonds, seismic waves, conductivity, experiments, and models to estimate the hidden inventory. The minerals may have capacity for several ocean equivalents, while the actual amount remains uncertain and uneven. What is certain is the cycle. Water moves down, changes minerals, and melting, and eventually returns toward the surface.
Even chemically bound water can influence the mechanics of the planet above it.
So the phrase "ocean inside Earth" is useful only if we remember what it really means. One reservoir flows in waves. The other is stored atom by atom inside rock. The next discoveries will come from smaller samples, better instruments, and clearer images of a world we cannot visit. The biggest question remains simple: how much water is actually moving through Earth's hidden mineral reservoir? The answer will reshape how we understand oceans, volcanoes, plate tectonics, and the long-term evolution of the planet. Earth is not hiding a sea beneath our feet. It is hiding water inside the architecture of the planet itself. That line connects rain, oceans, sinking plates, deep minerals, magma, and volcanoes across geological time. The familiar water cycle runs through clouds and rivers. The deeper cycle runs through rocks and tectonic plates. Deep storage can last far longer than any surface reservoir, even though the mantle itself keeps moving. Every journey through the mantle changes the mineral container and therefore changes where the hydrogen can go. That is why pressure, not empty space, creates Earth's hidden water reservoir. The reservoir is invisible because the rock still looks like rock. The water exists in the chemistry. A microscopic inclusion revealed a process operating across a layer thousands of kilometers wide. We know the mantle can hold oceans of water. We still do not know exactly how much it holds today. What lies beneath our feet is not a secret ocean. It is a hidden planetary cycle written into minerals. And that hidden reservoir may be one reason Earth has remained a water world for billions of years. The dinosaurs did not vanish in one explosion. Their extinction began with 24 hours that permanently rewired the planet. Before impact, life occupied nearly every habitat. None of it could sense the mountain already approaching from space. The object was probably a carbon-rich asteroid, roughly 10 to 15 kilometers wide and moving at extraordinary speed. Its size was terrifying. But size was only half the weapon. The other half was velocity. It crossed roughly 20 kilometers every second. At that speed, an ocean becomes almost irrelevant. Its destination was a shallow tropical sea near Yucatan, a target that amplified the catastrophe. Below the sea lay carbonate and sulfur-bearing rocks, materials capable of turning impact energy into climate-changing dust and gases. Shocked crystals, glass droplets, crater rocks, and global sediments preserve the event, like damaged frames from a lost film. There was no warning system, no evacuation, and nowhere on Earth prepared for what was seconds away. The atmosphere barely slowed it. Air compressed ahead of the asteroid into a descending wall of incandescent plasma. Near Yucatan, the horizon brightened beyond sunrise. Animals had seconds between noticing the light and being overtaken by it. From the upper atmosphere to the surface took less time than a breath. Then the Cretaceous world changed forever. Contact released energy near 10 to the 23rd joules, far beyond every weapon humans have detonated. The asteroid did not remain intact. It and the seafloor were crushed, melted, and vaporized almost instantly. Crater geometry suggests a steep, oblique strike, an angle efficient at launching vaporized target rock into the atmosphere. Ordinary minerals became extraordinary evidence. Quartz deformed, sediment became glass, and ancient seabed entered the sky. Within the nearest region, survival was effectively impossible. Heat, pressure, debris, and wind arrived together. The explosion remained regional for only moments. Its fastest material was already climbing high enough to become a global disaster. The impact excavated a temporary cavity far deeper than the crater that would remain. Earth's crust opened like a wound. Before the crater finished forming, seismic energy was already racing through the body of the planet. Compressed crust rebounded upward. For a moment, solid rock rose